we can start.
Thank you so much, Adway, for this kind introduction. Thank you for the invitation. I'm disappointed that I couldn't be there, but I'm glad I'm able to speak to you all and hopefully interact with you all as well throughout the conference. Okay, so the title of the talk is Earth on a Chip, and the reason why I kept this title is because the whole point of doing AI-based modeling for our coupled Earth system, or at least some components of it, is to improve the computational cost associated with running traditional models. So the ultimate goal being that we would be able to deploy some of these models on edge devices might not be too impractical, although at this point of time it may be. So hopefully looking towards the future, the title of the talk was Earth on a Chip. I'm not able to see the chats when I'm presenting, but feel free to interrupt me if there's a question from the audience in person or online. I'd rather have it be interactive than me just talking about it one way.
Sure, if there is a question, I will let you know.
Okay, that's great. And I'll try to stop at 50 minutes and continue. There's two lectures, one after the other, one slide deck. So hopefully it'll be a nice continuation. Okay, so by now we all understand the major challenges of modeling our coupled Earth system. Most of you are climate scientists or Earth scientists in some aspect. I'm not. My background was that of a fluid dynamicist and a computational scientist, and I started doing machine learning about 6, 7, 8 years back. But the way I understand it from a modeler's perspective is that the system, just like any other multi-scale system, has its inherent challenges with the absence of scale separation. So the climate system is chaotic, nonlinear, high-dimensional, and along with that, it has this nature which makes it multi-scale. That's a trait that is shared with almost all turbulent flows, not just in geophysics, but also in engineering systems. And the reason why it's particularly difficult is not because it's just multi-scale in multi-physics, but because there's no scale separation in these systems. So what do I mean by that? So an example that I usually give for multi-scale systems that are much easier to solve is the projectile of a baseball. The ball in itself is made of a material, and when it's going through the atmosphere, when you throw it, and by the atmosphere I mean a few feet of distance, it faces winds, it faces a temperature gradient, although very little, and when we want to model the velocity of this ball, we don't really have to care about anything except for Newtonian mechanics, right? All we care about is projectile motion, despite the fact that the ball has chemical constituents and they're interacting with each other and everything else. And the reason why we don't really have to worry about it is because despite the fact that you can technically call it a multi-scale system, to understand the motion of the ball, we really do not have to understand quantum chemistry, and they're completely disjoint. Unless this ball is moving through air in a scenario where the temperature is changing so rapidly, or in an environment where the temperature is so large that things happen, we don't really have to care about the other aspects of physics or the chemical physics inside the ball. So we can just model the mechanics of the ball and be able to decipher how far it would go or what would be the motion of the ball. So despite the fact it's a multi-scale system, you don't have to care about all the scales in that system. Turbulent flows, on the other hand, one of the fundamental challenges in atmospheric modeling is very different. And the difference here lies in the fact that the scales interact with each other. You cannot call something large scale and be able to say that, okay, I'm going to model only the large scales and completely ignore the small scales and get away with it. In most practical scenarios, we do something very similar to that at a large cost, but generally you can't get away with it, right? Because of the nature of turbulence, the smallest of the scales interact with the largest of the scales and the other way around. So to be able to fully resolve a system with no scale separation, you need spatial and temporal grids, so spatial temporal resolutions that are high enough that it resolves all the physical processes up to the smallest ones. And the climate system generally has physical processes that go from a few micrometers to a few to several thousands of kilometers up to the radius of the Earth. So those are the spatial scales of the physical processes, and then we lovingly cluster them into maybe 4 different scales: micro, mesoscale, synoptic scales, and large scales. Similarly, we have processes that have temporal scales going from seconds to years. For example, in the previous talk, we heard about ENSO and MJO, which are of the timescales of either years or months in case of MJO, while there are where there's turbulence convection, which are super microscale processes. The thing is that both of them are interacting with each other, and you can't ignore one to model the other. You can't model ENSO without understanding atmospheric turbulence, or by completely disregarding atmospheric turbulence. So that's the major challenge. But at the end of the day, we are basically solving a coupled nonlinear partial differential equation where you have large scales and small scales. It's just that they're so tightly coupled that you can't solve them separately without actually accounting for their coupling. So that's basically the major challenge in doing climate systems. And from here, I'll probably get into why I'm talking about all of this, why I'm talking about multi-scale physics and turbulence, and why any of this matters when we're thinking about machine learning models that represent them in some way or the other. Now, having said that, over the past few years, a big part of the initial portion of this talk is a little bit of history of climate and weather modeling. Maybe some of you are really familiar with it, but I still find it interesting because it sets the backdrop of how modern day AI, modern day deep learning is useful in this context. So this is a plot from a 2017 paper by Tapio Schneider, and what he was trying to demonstrate through this plot is how much of the resolution of Earth system models have increased over the years. What is the associated floating point operation, so the computational cost in some measure, and what are the physics that it's really resolving by increasing the resolution. So unlike engineering turbulence, which only focuses on Navier-Stokes equations, that's it. The Earth system model is coupled physics, right? It's not just momentum equations, but a bunch of other things associated with it. So increasing the resolution doesn't just mean that you crank up the number of grid points. It actually means that if you're increasing the resolution, it means there are certain physical processes that you're explicitly resolving, which means you're writing the coupled partial differential equation associated with it. So today's traditional climate models are about 100 kilometers in resolution, right? That's the sort of the least count in these computational models. And then if you think about it, 100 kilometers is really not a high enough resolution to resolve anything. So an example of what is not getting resolved is, for example, convection, which to be able to resolve, you need to go to at least 10 kilometer models. Now, that doesn't mean that we don't have climate models that are running at 3 or 5 kilometers today. In fact, the ICON model is an example of a climate model that's 3 kilometer resolution, 3 kilometer horizontal resolution, and it actually completely convection resolving, cloud resolving model. But we don't have a 100-year, 100 ensemble simulation corresponding to these models. But basically, what this plot tries to say is that if you want to go to convection resolving zone, which is this gray portion, that's where clouds are resolved, which means that you get a good estimate of precipitation, which is at least one big uncertainty in climate models. You are looking at floating point operations that are off the charts. And think about running this for hundreds of years over 100 ensemble members. And I'll talk about what ensemble members mean and why it's important. But if you think about projects like the big Lens 2 projects, we're kind of far away from reaching that scale. On the other hand, if you look at shorter timescale models like weather models that are fundamentally solving the same equations with certain technical differences in terms of energy budgets and these things, we have had a quiet and steady progress, pretty steady at the same time slow enough. So over the years, we have been able to increase our weather models resolution to about 25 kilometers, 18 kilometers native grid for ESMWF's IFS. That's still not cloud resolving, That's still not cloud resolving, much better than climate models though. And the accuracy of forecasts have steadily increased over the years. So from 1980s to the modern day, day 3, day 5, day 7, day 10 forecasts, we have nailed down 3, 5, and 7 to the first order, maybe 3 and 5 to the first order. Our day 10 forecasts are still pretty bad. The northern hemisphere forecasts are better, which is the dark line, and the bottom ones corresponding to each color, the southern hemisphere forecasts. So we have had a steady improvement in the quality of forecast that we've been able to afford just by increasing the horizontal resolution of these models. So clearly, when it comes to weather modeling, resolution has a big impact. So if we just sit back and wait for 100 years and hope that Moore's law is going to catch up, then we're going to have bigger computers to be able to resolve them. AI sort of comes into that picture is because Moore's law is sort of plateauing since the last 5 years. So relying completely on hardware technology is probably not going to get us out of that plateau. Now, going to sort of the history of weather modeling and the impact of resolution, it's important to understand that 25-kilometer resolution is still not cloud resolving, and we still have major challenges with 25-kilometer weather models when it comes to predicting things like extreme precipitation and so on. So if we look at the era of climate modeling and weather modeling from 1949 to the modern day, we have had steady progress in terms of improving climate models, whether it's the physics that are getting resolved in the climate models, steady increase in computational cost that was a steady increase in computational cost that is coming directly from hardware innovation, and relying on basically what we have relied on for the past 100 years, which is first principles, partial differential equations, and then numerical solutions based on the kind of methods that the speaker right before me described through like fundamental improvement and knowledge in finite volume solvers, and on so the associated mathematics and finite volume methods and so on. But if you actually go back a little bit, about 1910 or so, and now if you think about 1910, we didn't have traditional computing per se. We still had computers, but these were basically people doing hand calculations on paper. They were still called computers though. So Richardson actually did the first numerical computation for weather prediction, and it was a complete failure because he wasn't able to stabilize his numerical solver. This was a handwritten numerical solver for the primitive equations, and he couldn't get it to be stable. Of course, he didn't back in 1910, because if you're somewhat of a fluid dynamicist or a numerical analyst, you would know that it was in the 1930s that Courant, Friedrich, and Levy came up with the very infamous CFL condition, which was sort of the cornerstone of how we stabilize this numerical solver. So Richardson really didn't know about CFL condition. Hence, he couldn't stabilize a model. He wrote an entire book about it though, but it wasn't a successful weather prediction per se. Now, moving forward to the 40s, basically the World War, there was this guy at Caltech, Crick, who was basically that time's data scientist. Well, data science wasn't a thing back then. It wasn't even an English term. He was a meteorologist, but he was one of those people who used ideas from data science to do sort of the first pattern matching based weather forecasting that was actually operationally successful. If you're interested in this story, and there are movies on it, Dunkirk is one of the movies that is based on this thing. He did something called analog forecasting, and I'll talk about it, which is to say, if you want to tell me what is going to be the weather pattern for 15 July, I'm today, say in 2025, I'm basically going to look at all 15 July weather since the time I have observational records, and basically take a linear combination or some combination of it and say that that's going to be 15 July weather today. So that's the idea of analog forecast. You look at past analogs of the variable that you're trying to predict, and you do some computation on it. You do linear combination, you come up with coefficients or whatnot. And that was very successful because that was the D-Day Normandy story, where they were able to basically win the war because he made a very successful forecast with it. So there was an idea back then that the ideas from that these theories from pattern matching could actually be useful and could be a direction for sort of weather forecasting or solving complex nonlinear partial differential equation. We all know what happened in the future is that Rossby basically pushed on the first principle ideas, and that is the direction that got traction. We couldn't really do anything useful with pattern matching beyond a one-off success back in the Normandy Day War. In fact, in 1949, the INAC supercomputer, which also made the atomic bomb, was used for the first time in a commercial, in a civilian application, which was to generate stable numerical weather forecast. That was John von Neumann, who used the INAC supercomputer to make the first ever numerical weather forecast, stable numerical weather forecast, and was also the first civilian application of the INAC supercomputer. Now, the reason I bring it up is because while Crick's idea was pretty interesting, Edward Lorenz basically wrote a bunch of papers that completely dismissed the idea, and it got removed from history. Unless you do a lot of analog forecasting in some other ways today, you probably have never heard of this idea. And those very famous papers back then was essentially telling us that if you really want to do successful prediction based on patterns, the number of analogs that you would need would be in the order of millions, and we simply do not have that kind of observational record if you want to do pattern matching on high-dimensional systems. Of course, the limitation there was people were thinking about analog forecasting in terms of regression or some sort of filtering or estimation ideas. They were really not thinking about nonlinear composition the way we do in deep learning. So the reason why pattern matching based deep learning works for the most complicated nonlinear systems today is because of its nonlinear composition. It's still the same. The idea is still rooted in analog forecasting, but the requirement of data was very conservative, a very conservative estimate from Edward Lorenz back then. In fact, in 2019, we wrote a paper on analog forecasting with deep learning for heat waves, where we were able to train this on a few thousand samples of data, and we could get very good prediction accuracies. So why am I talking about all this? Well, one is because I wanted to highlight that deep learning in weather is, or at least the roots of it, is not grounded in today's big tech bringing out big models like GraphCast, but it's actually rooted in history. People had been doing machine learning or whatever data-based methods since the ages. It just never got off because first principle methods were much more robust, much more rigorous, and in many ways, some people would say interpretable, although that can be questionable. Now, moving forward today for AI-based climate modeling, if you think about what are the grand challenges that we're trying to solve, if you're using AI to do some sort of climate modeling, whether it's parameterization, fully data-driven modeling, something else or the other, bias correction or whatever. What are the three grand challenges we're trying to solve? Well, climate models are great. They have 100 years of history. They work. They're operational. There are big centers running them. You and I can't just write a climate model in 2 days. Neither can we run a climate model if we wanted to. We need computing access. So what are the big challenges? Well, one challenge is that climate models are very uncertain. They have uncertainty in certain things that really mess up some of their estimations. Not everything. Some of these things, and the uncertainty comes from at least three important components of it. One is that they're 100-kilometer models to the large part, so they don't resolve a bunch of physical processes. So this is called as epistemic uncertainty, and these are basically all the approximations that go into representing the forcings of the small-scale processes on the large scale. So these, in climate model language, are called parameterizations, but it's really basically we don't know how to resolve convection, so let's just throw something at it. It does not have to be data-driven. It's actually inspired from physics, but that it comes with a huge deal of uncertainty, and uncertainty in things that are important to us, like precipitation, for example. The other source of uncertainty is a very reasonable one. It's not because of our incompetence. Well, you can think of epistemic uncertainty as sort of human beings' incompetence to either resolve convective physics or afford computational resources to be able to solve PDEs corresponding to that. But the scenario uncertainty, on the other hand, over here, is how much CO2 are we going to pump into the atmosphere in the next 5 years, for example. That's not a modeler's problem. That's not a scientist's problem. That's really on us, right? We don't know how much we're going to do. So that carries a lot of uncertainty. And the other one comes simply from internal variability. It's the fact that the system is chaotic. It means that if you want to say something about any of the variables reliably, you need a lot of samples. If you want to say that my extreme precipitation is going to be 3.5 standard deviation from the mean, it means that you really need to be able to resolve. You really need the number of samples, a large enough number of samples that you can resolve 3.5 standard deviation from the mean. And as you see, as we run climate models, as we simulate climate models into the future, the further we simulate, the more temporal samples we have, and the lesser this uncertainty becomes because we have more and more samples. So uncertainty due to internal variability disappears, right? While the further we go into the future, the scenario uncertainty, which is basically the impact that pumping carbon dioxide into the atmosphere is going to have on the variables of interest, are going to increase, right? Because you start off with a big enough uncertainty, and that's sort of propagating to the model. And epistemic uncertainty is actually decreasing over time. And if you're interested, I can tell you a little bit why this actually this happens, and the decrease with time of epistemic uncertainty has led to a line of literature called mixed precision computing, where you basically give up on some of the accuracies of these parameterization models, which are pretty bad in the first place, to get computation, like basically earn computation that you can then invest into increasing the resolution of the models. Now, this is not the complete story, because if you look at things like the Southeast Asian monsoon, or generally precipitation over Eastern Asia, which is obviously of interest to people in India. So basically, regional scale impact, this plot for uncertainty actually changes. In fact, it turns out that there's a big contribution of epistemic model uncertainty into how well we are resolving precipitation, and in fact, internal variability as well. So it's not that we look at the left-hand side plot and we decide what to do with AI, but this plot basically changes depending on what you want to look at and whether you're looking at it globally or you're looking at it regionally. So things like that are important when you're deciding sort of what is the best place to invest. If it's compute, if it's better models, if it's better physics, where should I invest? And that actually depends on what you want to resolve. Now, if you think about it, internal variability and carbon dioxide, the uncertainty that comes from these two, to be able to reduce this uncertainty, we need faster climate models. Why? Because we need more scenario exploration, we need more ensemble members, we basically need more data. More data reduces this variability. So if you have faster climate models, you can run them faster, you can run them for a larger number of ensembles, and that kind of solves your problem. While epistemic uncertainty, model uncertainty, is a different ballgame altogether. It's where you basically need to do better physics, or you need to build better approximation to the physics that you're not able to resolve. And that's not something that we're going to talk about, at least in these two lectures. Because I'm not going to talk about it, I'll spend maybe one more second talking about it. There's a lot of investment and from us and other people in various labs, where we've tried to build better parameterization schemes by looking at observational data that are completely driven by machine learning models, and they are indeed a better sort of alternative to sort of the ad hoc parameterizations that we have today. At the same time, development in this field of work has been rather slow, and the reason is multifold. One of them is coming from the fact that these models have a hard time being stable when interacting with the rest of the numerical solver. A small example of what we have done. Sorry about that. Small example of what we have done here is, for example, gravity waves are not accurately resolved in all the weather models basically, and the difference of it you can clearly see if you look at the wind profile. how different it gets if you resolve gravity waves and when you don't. And some of the things that we have done in the past is basically come up with better gravity wave parameterization strategies based on data-driven models, learning from sort of regional, very high resolution gravity wave resolving simulations, and then learning from there and putting it back into GCMs at 100-kilometer resolutions. Anyway, so these are things that people have been working on as well, and I'm sure you've heard a lot of talks about convection parameterization by Vishal and so on. Anyway, going back to the first one, which is faster climate models, that's basically all that I'm going to talk about. And talk about theory, I'll talk about application and so on. We've made a lot of progress here, and we've made a lot of progress in very little time. That's sometimes not the most the most optimal way of doing science. Basically, in about 2017, 2018, there was an Oxford workshop about a workshop in Oxford University, where a bunch of us doing machine learning for weather and climate got together, and they were discussing when can fully data-driven models. By fully data-driven models means that you have either reanalysis data or you have simulations from climate models, you have simulations from weather models. These are the data that you have at your disposal. Can we train machine learning models? Can we train deep learning models in whatever way? Physics, without physics, bells and whistles, transformers, it doesn't matter what it is. Can we build models that will perform at par or better than ECMWF's IFS, which was the gold standard, which is still the gold standard in weather forecasting. And the consensus that people reached to was that we're not gonna get there in the next 10 years. That was in sort of 2018. In 2022, some of us at Rice, Caltech, and NVIDIA released this model called ForecastNet. And what we really did in ForecastNet was that for the first time, and we were doing data-driven weather forecasting for a while. This isn't my first weather forecasting paper. But for the first time, we tried to scale up deep learning models at 25-kilometer resolution. So by learning from reanalysis at 25-kilometer resolution, which was the highest resolution commercially available or publicly available data set that we had on a bunch of different variables. So not just a few variables, a lot of other work, including mine. We looked at sort of lower dimensional atmospheric models, few variables and things like that, or looking at the UF projections of variables and things like that. But this time we did something very straightforward. We basically took 33 variables from 1979 to 2017 from ERA 5, and we trained what was back then a very large model, about 80 million parameters or so. It was called ForecastNet. And throughout the length of the talk, what you'd realize, it's not important what any of these models are. In this case, it was a vision transformer that was parameterized with a Fourier neural operator, which means that global attention that you have in transformers, they're quadratic in memory, right? They're n-squared operations. We basically replaced those attention modules with Fourier transforms, so we could scale at n log n. And the reason why did we do that? Because we were tackling 25-kilometer for the first time. And people just couldn't do it because of memory. So we were like, okay, let's tackle memory. So let's do something to fix memory. So that was ForecastNet. And what ForecastNet was, and what we realized is that ForecastNet was either at par with IFS for all the variables and could beat IFS for precipitation and other small scale variables. So precipitation is very easy to beat ERA 5 or IFS, is because none of these models are convection resolving. So precipitation is pretty bad in these weather models anyway. Now, the model was trained in this specific way, and some of you may be familiar with it, some of you may not be. If you have questions, just ask me. There are things I might assume that you just know, but probably it's your first time looking at it. The way the model was trained was you put the state of the atmosphere in, you predict something, and you match it against the state of the next time step. So probably not as simple as it looks here. We have a 2 time step tuning procedure and things like that. But roughly, this is what any of the data-driven weather prediction, AI-based weather prediction models are. It's one big network, absolutely material what that network is. If you're Google and you can train trillion parameter models with TPUs, then you will use a trillion parameter graph neural network. If you're a professor at a university, you can't afford TPUs. So you'd have to resort to something more efficient and come up with clever ways to scale things. But it's immaterial what this model is. As long as it's big enough, it follows the deep learning directive, right? That if it's big enough, it would work. And that's exactly what we did. We just had a big model that was trained to predict the next time step. What was important is that there was no physics in these models. And at least for 4 years leading up to ForecastNet, including myself, we invested a lot of time developing things that were physically consistent by construction. So we thought about things like equivariance and rotation and vorticity, mass budgets, etc., etc. All the things that a typical climate scientist would talk about, and all important things. When you're running these models, do they satisfy energy constraints? Well, no one put them there, so you should think about cleverer ways to put things there. And not just in weather forecasting, even for other applications in science and engineering, if people were doing fluid mechanics and the problem was incompressible, then they would come up with all these absolutely rigorous strategies in neural networks to enforce continuity equation by construction, and these were amazing models with the right physics constraints, and we always thought that was the way to go, that weather models, AI weather models, are going to become better. They're going to be at par with physics-based models when we start thinking about physics and putting them into the AI weather model. What we did with ForecastNet was the exact opposite. This model has no semblance of physics whatsoever. It's just data and a really giant model. And it was outperforming IFS without doing anything extra. Since ForecastNet, at least 2 big models came out. One of them was Pangu from Hawaii, and one of them was GraphCast that you've probably heard about a bunch of times from Google DeepMind. Again, the great thing about these models, well, you can argue whether it's a great thing or a bad thing. The easy thing about these models are that you don't really have to care about any of the physics. You don't even have to be a climate scientist or even a physicist to be able to train these models. You need a lot of money to buy GPUs, but you don't need to have a physics education to be able to train these models. You just need to train it on a large amount of data. And for these models, they showed that comprehensively they were beating IFS for 10-day, 5-day, 3-day, 1-day, whatever lead time you're looking at. They're comprehensively beating the best numerical weather prediction models on any of the meteorological metrics that you look at. More recently, ECMWF operationally runs a version of GCAS that they called AIFS, which is also a graph-based model. And that operational model, AIFS from ECMWF, is actually better than their IFS. In fact, it's better than IFS ENS, which is a heavy-duty version of IFS with ensembling and so on. I put in these plots here because these are not just statistical metrics that people are looking at. They're looking at tracks of hurricanes and so on, and it captures them better as compared to observations than numerical models. So there was really no catch. It was a true success story, and probably the only other success story in deep learning for science or AI for science after AlphaFold was probably weather forecasting, where there was operational efficiency to be gained through like a purely AI strategy. There are lots of AI for science works and a whole bunch of papers around it. This was beyond just research papers. This was really operational. At least in Silicon Valley, there are probably 20 startups that are now using these models to do risk and this and that and whatever else, because it's cheaper. It's orders of magnitude cheaper. You can basically run it on a laptop. It's that cheap in inference. So you really get a lot out of these models. So that's the success story. Now, the general approach to training any of these models is that you are trying to solve this nonlinear differential equation, right? Coupled nonlinear PDE that I'm writing it out in this simple way. And numerically, this is what you solve. This is what you solve in a climate model. You solve your X is a high dimensional vector, G is the nonlinear operator that has advection, diffusion, a bunch of other parameterization stuff, and you solve it with numerical methods. Essentially, what you do in a climate model is that you estimate G, which is the tendency, and then you integrate forward with some numerical time integrator. What these models are doing is that they're replacing the entire right-hand side with a giant neural network. That's essentially what they're doing. And then they're training it on some version of this L2 loss function. That's really it. Now, the problem with this approach, and this is not a problem operationally, this is more of a scientific philosophy problem, is that now every day or every 15 days, there's some paper coming out that says, okay, now we have 0.2% better accuracy as compared to GraphCast because our N has these extra 2 attention layers. So these are the kind of stuff that happens. And it has happened in the ML community as well, right? People have a benchmark, they want to beat the benchmark, so they do whatever they want to beat that benchmark. The problem is we don't know why any of these changes have an impact. And that's really not the way science worked, at least until machine learning came into the picture. And then we had some discrepancies. The discrepancy was that if you train a model to directly go to 10 days, like predict 10 days, you basically have a more performant model. A model that is trained to predict every 10 days has more accuracy than a model trained to predict every day. Now, from a numerical analyst standpoint, that makes absolute zero sense. Smaller density leads to a better numerical model. That's what I've learned, that's what you've learned. Suddenly it doesn't make sense in the context of machine learning anymore. So that's where sort of this talk begins. Can we reconcile with some of these issues? Rather, first we want to ask a first order question. Is the story really as clean as it sounds? That these AI weather models are going to change this industry, once and for all. So this is from a paper maybe a year and a half back. What we did was we took all these really remarkable AI weather models, including ours, which was ForecastNet. There was a V2 version, which uses spherical harmonics and so on and so forth. And then we ran it. We just decided to run it for more than 5 days and more than 7 days. So the first thing that we notice is that some of these models blow up. They are just outright unstable. Now, now here's a problem with models such as these. If you think of these as CFD models, like computational fluid models, and it's a little more than that, but computational models, you don't go and say that my computational code is stable for 1,000 time steps. That's not a feature, that's a bug. If it's unstable after 1,000 time steps, you have a problem with the model. It's not, you can't ship a model that is stable for 1,000 time steps and you have a condition, hey, run it for 1,000 time steps, that's it. If it's unstable, there's something wrong with it. That's why it's unstable. It's not supposed to be unstable. We learned about CFL conditioning in 1930s. We know how to stabilize numerical models, no matter what they are. Now, there's another level of problem. The other level of problem is that some of these models are actually pretty stable. And if you're not a climate scientist, you look at these Z500 and zonal wind patterns, you'd say, these look reasonable. This is how pressure should look like. Like if you look at the upper panels, you don't have to be a scientist to know that the Earth shouldn't look like this. Like in no time would Earth look like this. But if you look at these patterns, you'd say, these look reasonable. It's cold in the Arctic. It's warm in the equator and the extratropics. The sort of, it's getting. So, but if you then these are stable models. But if you look at them a little more carefully, you'd realize that, okay, they're actually not right. Why? Because if I look at a 10-year climatology derived from these models, and some of these models are not there on this plot because those were unstable, so you can't get a climatology. But if you look at the mean Z500, for example, all the other colors except for black are the different models. None of them really match Z500. And there's some crazy stuff going on in the poles. Now you look at zonal wind, this is even more concerning at 250. You see that some of these models show that zonal wind at the equator is 20 meters per second. Now we would die if we had things like that happening. It's supposed to be zero wind. So even though it's stable, it's very unphysical. And this is a unique thing now that we have learned in machine learning, that it's hard to find a computational code that is stable and has the wrong energy unless you really mess up somewhere. If you're wrong somewhere, it would eventually lead to a blow up. But this is something that we have seen before in autoregressive models. These are hallucinations. If you have dealt with language models, this happens all the time. Except when it happens in language, no one cares. We just complain and post on LinkedIn that ChatGPT is bad. But when it comes to operational settings, these unphysical hallucinations actually have a big impact. So the goal is to sort of understand where this is coming from, get a theoretical basis for it, and then sort of build principal structures around it so that these things don't happen. And that's why we say that, can we build principal structures in N? It means that I don't care about N, because the game of building a better N is going to lie with people who have the largest GPU resources. So whatever theory that we develop, it should be independent of N. Like linear stability theory in PDE analysis does not, well, at least to the first order, does not care about whether you're doing weather and climate with your PDE, or you're doing combustion with your PDE, or you're doing plasma with your PDE. The theory is agnostic to the underlying system, to the first order. This is not entirely a true statement. But for us, this is really what we want to do. We want to build theory that is agnostic of N, because every day there will be a new N, and it will be a better N for whatever reason that we can't explain. So our theory needs to be robust to that. Now, the way science has always worked for us is that we are a theory first kind of a field. At least most of the engineering that I've done. There are things that are not theory first, like quantum chemistry was not theory first. It was empirics first, and then, but generally we have built good first principle theory. We have done hierarchical modeling, especially in Earth system, and then we have validated with observations that have improved both our theory and it has improved our modeling approaches. And this is grounded in something called reductionist sciences, right? We want parsimonious generalizable model. We want models that work for baseballs, and we want the same model to work for planetary motions. And that is the amazing thing about Newton's laws. F equals ma is the best machine learning model, because first of all, it's a machine learning model, right? It's not a first principle model. F equals ma is a great machine learning model because it has one parameter. It works for baseballs and planets. So that's what, as scientists, we aspire to do. We want to build general models. The way the ML community has worked is a little different. We have come up with algorithmic intuition, and then we have done hierarchical modeling. And based on that, we have tried to distill theory out of it. And finally, we have tried to implement things at scale. And that's sort of the approach that we have taken as well. Basically, the same reason why deep learning theory is not caught up to engineering applications in deep learning is because it's so hard to build a theory around these models. So what we don't actually build first principle theory, we try to distill theory out from observations, or rather, modeling experiments. So hierarchical modeling in the context of ML is where you try to reproduce exactly the same principles of hierarchical modeling in Earth system, except with the machine learning models, and see if there's a theory that sticks to it. And then the grand challenge would be, let's scale it up, for a full-blown climate model and see whether this theory holds up, because a theory is only as good as it scales, right? Even if it's very rigorous, very nice, and like for example, theories around physical constraints and rotational invariances, they're great theories that we have built into machine learning models, except we never needed them. Experimental observations tell us if you have large data, large models, you don't need any of that stuff. So it has to be theory that really scales. So that's pretty much the approach that we're taking. So why are these models inconsistent, and why are they unstable? And the reason is because they have a problem called spectral bias, which means that if you look at the Fourier spectrum of any of the variables, you'd realize that their spectrums do not line up at all. In the true spectrum of error 5 is the black line. Every other color is every other state-of-the-art model. At day 10, you basically have, some of these models are blowing up, like this model. Energy is increasing. Some of these models are diffusive, but none of them are accurate. None of them get the scales right by day 10. And you may say, well, day 10, you're pushing it, man. Well, how about the first delta T of prediction? If you look at the first delta T of prediction from any of these AI weather models, you'd realize that it only captures 1/4 of the wave numbers. And these wave numbers calculated with the spherical harmonics. Now, what this really tells us two things. One, these models don't get small scales right. For whatever reason, it doesn't get small scales right. So let's figure out why later on. Secondly, it tells us that even though we think that we are doing prediction at 25-kilometer resolution, we're actually doing predictions at 1/4 of that resolution. So you have a very coarse resolution weather model, despite the fact that you trained on 25-kilometer data, because the rest of your scales are just garbage. You've got it wrong right from the beginning. So you get the synoptic scales right, that's about it. But that also tells you why these models got so much success. It's because if you look at weather prediction metrics, they're all dependent on synoptic scales. RMSE, ACC, all these metrics, they're so biased by the large scales that no one, your RMSE doesn't change when your variable has a power of 10 power minus 7. So you get these scales right, your metrics are going to be off the chart. And that's why you think that these models are so good, but they're so unphysical because they got all these scales wrong. And digging into it further, it's just not an AI weather model problem. It's a problem everywhere. In fact, it's a problem generally with deep neural networks. And now we're going to get into the theory of it. It's a problem with deep neural networks trained on anything, even cats and dogs. You never get the small scales right. To classify a cat as a cat, you don't need to get the small scales right. You just need to get an overall picture of a cat and you're good to go. For turbulence, that doesn't work. Why? Because if you don't get the small scales, you get an incorrect energy cascade, and then you're either doomed to blow up or you're doomed to diffuse to zero. So that's why any model on any system, if it's multi-scale, you're basically doomed by this problem. This is called spectral bias. Now, to ensure that, okay, so now this is what we're going to do. We're basically going to build, a scientific theory to machine learning based modeling of the physical sciences and sticking to Earth and climate here. And these are two papers that you can read if you want to look at more of the details. I mean, I'm going to talk about the details anyway. So the first section of it is algorithmic intuition to hierarchical modeling. We'll first explain spectral bias, derive it, and then we're going to build something to fix it and so on. And then we'll do some hierarchical modeling, see whether we can at least fix it for intermediate complexity systems. And then we will go to the other boxes that were here and then here. So for that, let's look at the 2D quasi-geostrophic system. Why are we looking at 2D quasi-geostrophic system? First, someone can come and tell you is that you're not looking at all the variables. That's why you have this blow-up problem. You have poles that you have not represented. Like one huge thing about AI weather was that you don't represent the poles properly in Cartesian code. You need to do regridding, and none of that matters. Deep learning doesn't care about any of that stuff, and this is how we'll prove it. This is a rectangular coordinate system. It's a box. It's a periodic box. Simple system. Only two variables. All the physics is known. All the states are known. No issues with the poles. We will first recreate this problem over here as well. So we didn't do anything fancy. We trained a unit to predict this system. It would show amazing accuracy. 4.8 hours accuracy is 97% correlation. You get all the snapshots correctly. Look at the Fourier spectrum. You're off by half the wave numbers. And if you keep autoregressively predicting with these models, so you take this predicted state, you plug back into this model, there would be an inverse energy cascade, right? It's 2D flow. You'll have an inverse energy cascade, and slowly this cascade is going to take your error to the larger scales, which would eventually lead to an instability. So that's the mechanism by which you see instability in any autoregressive model. For autoregressive models defined in continuous space for physics and so on. Now, if you want to derive spectral bias, the way to do this is first derive it for a single layered model and do mathematical induction for the rest. So I'm going to quickly gloss over it. If any of you are interested in the math, just stop me and I'll go through the details. So the way to do this is very simple. You assume you have a single layer, your weights and biases, W and B, your input is U, and the output of your layer is HU, okay? And then you have a tangent hyperbolic nonlinearity. So you write it out. You saw this equation in the previous talk as well. Tangent hyperbolics, and then what we're going to do is we're going to represent everything in Fourier space. So we're going to go back to our first year engineering mathematics class. We're going to do fast Fourier transform, or in this case, we're actually going to do Fourier transform with pen and paper on both the left-hand side and the right-hand side. To do that, these are simple linear operations. You need to know what's the Fourier transform of tangent hyperbolic. ChatGPT says it's this. So we're going to stick to this. And then we take we plug this back into this model, and finally we get the Fourier transform of H, which has this nasty looking expression. So now the expressions are going to get a little nasty, but it's easy to keep track of it. The only thing to keep track of is that there's an exponential ik term and an exponential negative k term here. So then we will define the loss function. The loss function is some target function f, its deviation from h, let's call this deviation, and then let's write everything in Fourier space with an amplitude and a phase. I'm assuming everybody here is familiar with Fourier transforms and so on. And then to get the total loss, what you'd have to do is you have to integrate this deviation across all the k, right, from minus infinity to infinity. So that's how you'd get the, so you'd use Parsifal's theorem and you'd basically get the full loss across all the wave numbers. Then what we would do is we are going to track the training of this neural network with respect to its parameters. What are the parameters? It's weights, biases, and the last layer's weights A. So it's a two, like it's an input, there's an input and there's a hidden layer and there's an output. So there are three parameters here. So how do we train models? We say we're going to compute the gradient of the loss function with respect to theta and then initialize theta with something, and then theta moves along the direction of the gradient. So the first thing we need to do is we need to compute the gradient of L with respect to theta. So this is a nasty bit of computation, but with respect to A, it would look like this, where this is what this big epsilon 0 looks like. It's the sine of weights ak and then exponential of minus k. So these expressions are not important, but the expressions are going to get a little nasty going forward. So one page of calculation and bringing them together, what you would eventually get is that the gradient of your loss function with respect to your parameters is ak. I'll explain what this is, an exponential minus absolute value of k, and this f term is basically order 1. This is unimportant. This does not depend on anything. Now, what is A? A is basically, in Fourier space, the deviation between the predicted value spectrum and the true spectrum. In a situation like this, the value of A is very small. Why? Because all turbulent flows have decaying spectrum. The power of this point is 10 power 3. The power of this point is 10 power minus 7. So the difference here is basically at the order of 10 power minus 7. So A is a very small quantity. When wave numbers are large, exponential of minus k is a very small quantity. So you have two very small quantities multiplied with each other, which means that del L del theta is essentially 0. So during training, as you keep capturing the large scales, your gradient becomes closer and closer to 0. And what happens is that you fail to update the parameters theta of your model. That's why training stops by the time you have captured the large scales, because the theta cannot move anymore. The gradient descent algorithm moves theta along the direction of the gradient. If the gradient is 0, theta stops. So you always have this bias, and this bias will always be there. Now, if you really think about it a little, if this was not turbulent flow, but this was a cat, then the difference between the true spectrum of a turbulent flow and the true spectrum of a cat would be that the cat would have no slope. It would be a flattish spectrum. When you have a flattish spectrum, your AK value would be larger, even if you have captured the low wave numbers. That's why del L del theta would still have non-zero values, and you can push further in a cat. So the more decaying your spectrum becomes, the worse your neural network is going to behave. That's why we have problems with turbulent flows. So if you look at an AI weather model and look at the spectrum of humidity, you'd see that you don't have a lot of bias because humidity has a flatter spectrum. You look at the spectrum of U250, you'd see it's really bad. So it really depends on which variables you're looking at. So now someone can go and only run a model with those variables that have flatter spectrum and then get stable simulations. So these are some of the ways to get away with instability. But this is the underlying problem behind the physical inconsistency. Now, if you have a model like this, you integrate it, you plug it back into, like you plug the prediction back into the model, this error is going to grow. So temporal error growth is determined by spectral bias and how quickly the error grows, generally from the model. Does this make sense to everybody? Any questions so far?
Questions from the audience? Yes, Dipan.
Hello, sir. I'm Dipan Chakraborty from IIT Kharagpur.
Hey.
Can you please again demonstrate that how to solve the spectral bias problem?
Yeah, I have not talked about how to solve it. I was just demonstrating the spectral bias problem so far.
Okay.
Just the problem so far.
Okay.
Okay. Now I'll tell you how to fix it.
Anyone else? Any other questions from the audience? Okay.
Okay.
So Ashesh, so like since it's a two-part lecture, so do you want to take a break now? I think we can have a coffee break here also.
Sure, go ahead.
Okay. So maybe we will return in another 15-20 minutes or so.
Okay, sounds good.
It would have been great to have you joining us for the coffee break. But nevertheless, thanks for a really informative talk. I really learned something about the spectral bias thing. Also,
Thank you so much. Thank you so much.
I also noticed that you have been generally online during many of these talks, and you have been asking questions also. Really appreciate that.
Yeah. I wish I was able to come in. Unfortunately, I have a bit of a visa situation as with many of us here. So
Right. You are right now. Where are you in India or US?
I'm in the US. I'm in California. So
Okay.